Welcome to our newest video session in which we introduce the function essential limit theorem. We start with a reminder on the modes of convergence that we have for random variables. So let xn be a sequence of random variables and let x be another random variable that serves as a limit for the sequence, all on a joint probability space omega fp. Then we have four possible modes of convergence. Firstly, the almost true convergence. So we say that the sequence xn converges to the random variable x almost surely or with probability 1 if the probability of all outcomes for which the sequence xn converges to the limiting random variables x has probability 1. Next, we have the convergence in mean square. So we say that the sequence xn converges to the random variable x in mean square if the expectation of the squared deviation of the sequence xn from the limiting random variable x equals 0 for n to infinity. So the mean square deviation vanishes. Weaker than both of these modes of convergence is the convergence in probability. It is implied by the two other stronger ones. So we say that the sequence xn converges in probability to the random variable x if the probability that xn differs from x by more than epsilon, if the probability of this event becomes asymptotically 0 for all possible epsilon larger than 0. So the big difference between convergence in probability and convergence in mean square is that for convergence in probability we only look at the outcomes for which we have more than epsilon deviation. So the size of the deviation, how much xn deviates from x, if it is more than epsilon, does not matter. So here the convergence in mean square, in contrast, puts large weight to very large deviations. So it is harder for a sequence of random variables to satisfy the convergence in mean square. And actually, by the Chebyshev's inequality, one can show that the convergence probability is implied by the convergence in mean square. So we have that the probability that xn minus x is larger than epsilon is bounded by the Chebyshev's inequality by the mean square deviation divided by epsilon square. The last mode of convergence is the convergence in distribution. So we say that the sequence xn converges in distribution to the limiting random variable x if the underlying distributions converge, and that can be described in different ways. So one way, for instance, is that the mean of the function f of xn converges to the mean of the function f of the limiting random variable x, where f is a bounded continuous function. So using bounded continuous functions is a sufficient criterion, but in order to understand this a bit better, we can look at results so that actually, for instance, if we take indicator function, which can be approximated by bounded continuous functions, then this convergence here actually becomes a convergence of probabilities. So it follows that all these probabilities must as well converge. In particular, so the problem is that one cannot take arbitrary A's, but only sets A's for which here in the limiting probability distribution we do not have probabilities on the edge of the set A. So in the one-dimensional case, we in particular can express that in terms of the CDF. So the probability that xn is smaller or equal to x, that is the CDF of the random variable xn, and that converges to the CDF of the random variable x, which is the probability that x is smaller or equal to x. And this must hold for all x for which f is continuous at x. So the convergence need not hold at every single point, but only at the points of continuity, which of course is the majority of points. We only can have countably many points of discontinuity, and at those the convergence need not necessarily hold. However, it should be clear that as the CDF is right continuous, even so if the sequence of CDFs here is not converging to the exact value of the CDF at a jump point, the distribution, the limiting distribution, however, is by right continuity uniquely defined. So this mode of convergence still completely defines the limiting distribution. So to start with the function essential limit theorem, we consider a symmetric random walk. So we have random variables xi that are independent identically distributed and can take the values 1 and -1 each with probability a half. Then it is clear that we have, as the values 1 and -1 are symmetric about 0 each with equal probability, that the mean of the xi equals 0, and we can easily compute that the variance of the xi actually is 1. So this means that the xi here actually are standardized. We call a random variable x standardized if it has mean 0 and variance 1. Then if we sum the xi, we obtain a symmetric random walk. So yn is the sum of all the xi from 1 to n. So the sample mean of the x's can be expressed as 1 over n, the random walk. And we know from the essential limit theorem that the sample mean standardized. So in that case, we already have mean 0, and since we have variance 1 for the individual xi's, the sample mean has variance 1 over square root n. So that means if we multiply by square root n, we have, by the central limit theorem, convergence to the standard normal distribution. So this means here that we have yn over square root n being asymptotically standard normally distributed. Now, instead of summing over all random variables here with the same scaling, we can also look at partial sums over fractions t, where t is between 0 and 1. So, for instance, t could be a third, a half, 3/4. If we only sum 1/3, a half, or 3/4 of the observations or random variables xi that we have, starting from the beginning I equals 1. So we can express that. So if we denote the largest integer smaller equal x by this square bracket of x, then we have Tn being the exact fraction of n. However, we are only allowed to use integers here in our symmetric random walk, as we cannot sum half of a random variable. So we have y at square brackets Tn being the sum from I equals 1 to square brackets Tn, which is an integer of the xi over n, square root n. So again, this, by the central limit theorem, converges to a normal distribution, but now with the variance of t. So that becomes clear if we do a proper standardizing here. So by the central limit theorem, standard central limit theorem as we know it, we can also express that in this form. So here we have now, as we only have Tn random variables summed, we accordingly, the variance of the random walk is Tn, and we divide by square root Tn by the standard deviation. So this converges in distribution to a normal distribution, standard normal distribution. And if we now want to look at this process here, this is simply obtained by multiplying through by square root t, which then cancels here with the square root t in the denominator. And that means that we have this limiting standard normal distribution also multiplied by square root t, which then equals normal distribution with variance t. So it follows that since this is the marginal distribution of the Brownian motion at time point 1, where this is the marginal distribution of the Brownian motion at time point t, it follows that our process ytn, which is the random walk at time square brackets tn divided by square root n, that this process here converges at all time points to the corresponding Brownian motion at that time point. We can, using a multivariate version of the central limit theorem, also show that actually all finite dimensional distributions of this process here, defined in terms of our symmetric random walk, converge to the corresponding finite dimensional distributions of the Brownian motion. So does that already imply that we have joint convergence for all time points t? So again, we are interested in the complete process. We want convergence to the process, and for that, of course, we need not only show established convergence for finitely many or countably many, but actually for all time points. And indeed, the answer is yes, and this result is the so-called Donsko's theorem, or also called the invariance principle. So if we have more generally a sequence of random variables independent and identically distributed with mean 0 and variance 1, and we define the partial sum process ytn as the partial sum of the xi's standardized by square root n. So that means that this process at the right endpoint of the interval t equals 1 has variance 1. Then the Donsko's theorem says that this process here, defined in terms of these partial sums, converges to a Brownian motion in distribution. And importantly, this means here convergence in distribution as stochastic processes, so jointly for all time points, not just for a few. To come back to our symmetric random walk, we have exactly the situations of the conditions of Donsko's theorem satisfied. So our random variables are independent, identically distributed. They have mean 0 and variance 1. We have here the random walk being actually a partial sum process or a partial sum. Or here we have partial sums of this symmetric random walk. Then this process yt being rescaled by dividing by square root n exactly is asymptotically Brownian motion. So to look at this, we want to approximate a Brownian motion by this sequence of symmetric random walks. So here we have a sample path of a symmetric random walk. So each time, at each time point, or over each time period, the symmetric random walk goes up by +1 or -1. So here this is not a complete faithful representation. Actually, the symmetric random walk stays constant over the intervals between two time points, so it should be actually rather look like this. But this is easier to draw, and we will also see a modification of this piecewise linear continuous representation. So in order to approximate or have convergence to a Brownian motion, it is clear that we need to change the scaling of both axes, because here the process only moves, it's piecewise constant over intervals of length 1. So definitely we will never have a Brownian motion, as a Brownian motion changes at each instant of time. So in order to have a faster changing, we basically rescale here that the right endpoint always becomes 1, and then of course this becomes 0.8, 0.6, 0.4 as the time, 0.2, and the starting point 0. And if we had 10,000 observations, we would still rescale it in the same way to the interval 0, 1. So the complete symmetric random walk, as we observe it over as many time points as we currently have, will be rescaled on the interval 0, 1. Now the next scaling is that at the right endpoint we want to have a standard normal distribution, so the variance of the symmetric random walk must match the variance of a standard normal distribution. Now here the symmetric random walk with 100 steps, each step having a variance 1, has a variance of 100. So the standard deviation is 10, and we have to rescale the vertical axis by a factor 10, so divided by 10. So that gives us here 3, 2, 1, 0, 1. And we know that the standard normal distribution is indeed more or less, so to 99%, distributed between 3 and -3. And again, this rescaling is needed in order to cancel out the discrete steps by which this process moves between time points. So at each time point it jumps by exactly 1 or -1, and the Brown motion of course needs to be continuous. So these steps must in the limiting process be diminished. And we do that by scaling them down, and we scale down in exactly the by a factor that guarantees that in the limit we have here a proper variance of a standard normal distribution. As an example, we can look at the multivariate binomial model for a stock price. So binomial distribution and the symmetric random walk we can simply express. So here if we have y100, so 100 of these steps added, we can, so that is say xi equals 1 to 100. Then we can express that also in terms of binomially Bernoulli distributed random variables, taking values either 0 or 1, with each with probability 1/2 for the symmetric case, 100 here, and the xi tilde are binomially distributed parameter 1.5. So the same here, we can either, for our multivariate binomial model for stock prices, for instance, if you're interested to model the stock price over an time interval from 0 to t, then we divide the total time in n periods, so that would be n periods for our binomial model. Then each period has length delta t, which is the total length t, capital T over n. We have an initial price as 0, and in this model, at each period the stock price can either go up by a factor u or down by a factor d. In principle, both factors actually can be larger than 1. So both would be up, but usually one will be larger than the other, and we call that then usually the up and the other the downturn. And also in the typical binomial tree representation, we can see that this is up and down in the tree, even though the actual value here might be larger than the initial value. However, in the financial applications, it turns out that actually the risk-free increase of money must be somewhere in between. So in order to avoid arbitrages, the stock must have one state that gives more than the risk-free asset and one state in which we have less outcome than for the risk-free asset. Otherwise, we could always, for instance, if both instances would be above the risk-free asset, we could simply finance our stock by taking debts, so go negative in bonds, have stocks, and then we would have a higher yield for the stock by which we could pay back our debts easily, and the remaining difference would be, which would be guaranteed to be there, would be our arbitrage. So actually, as today we have risk-free rates about 0, we can really speak of an up and a downturn. And one particular scenario would be, parametrization is where u equals exponential function to mu delta t plus sigma square root delta t, where sigma stands for the volatility of the stock price and mu for the growth rate. So this e to the mu delta t factor is present in both the up and the downturn, and then we have the risky part where we have e to the plus sigma square root delta t in the up and e to the minus sigma square root delta t for the downturn. Then we can express at time t the stock price as the initial price times e to the mu t, so that would be the deterministic growth according to this growth part, and then plus the random noise sigma times square root capital T times our standardized symmetric random walk as on the previous slides, and this process here converges to a Brownian motion and in distribution, and by the continuous mapping theorem, as taking the exponential of this function here, this continuous mapping, we actually find that this process St converges to a geometric Brownian motion, where we have here the standard Brownian motion, or re-expressing this in the original time t, we have b tilde standard Brownian motion on the interval 0 capital T, where this is a Brownian motion on the interval 0, 1. So the continuous mapping theorem says, we have that in the problems of this week, that if we have a convergence in distribution of random entities, so this could be stochastic processes, simply random variables. So if we have xn converging in distribution to x, and we have a continuous function that need to be continuous at the possible values that are here involved in these random variables, then we have that g of xn converges to g of x. And again in distribution. So as a technical remark, it seems from what I said, how I introduced the Donska's theorem, that convergence here in our example, convergence of the finite dimensional distributions that we have here by the ordinary central limit theorem is completely enough to have also this functional convergence. Actually, it's not as simple, so definitely the convergence of finite dimensional distributions is necessary, but it's not sufficient. We additionally need conditions that are called uniform tightness or stochastic compactness that are certainly beyond the level of this course. And for instance, uniform tightness follows from starting point 0 having this stochastic equicontinuity condition where we require that the probability for the process, the nth process in the sequence, that if we look at the process at two different time points being not more than delta away, that for such points we have a deviation larger than eta, that this probability is smaller than epsilon, at least in the limit. Okay. Again, we won't use stochastic equicontinuity, but it should be at least pointed out that for in general to show convergence in distribution for stochastic processes, we cannot just rely on convergence of finite dimensional distributions. That can go wrong, and we'll actually have an example in just one of the next slides. Before we come back to our graphical representation here, where actually for ease of representation we used linear interpolation. So while the two symmetric random walk as defined stays level over intervals, so here it would have been something like this. Etc. It gives a nicer representation if we simply take the beginning point and end point of such an interval here of length 1 and interpolate over this interval the random walk by the endpoint, beginning and end point. So if we have a situation like here, we have at one time point this value, and then at the next time point this value, then we simply use a linear interpolation of these 2 points. So if then it goes up again, then we would have not this piecewise constant form here, but actually a triangle. So here we can see plus minus 1 alternating, and we represent that in this piecewise linear fashion, or not piecewise constant. So that gives a nice continuous function, which of course is a better approximation for a continuous stochastic process like the Brownian motion. So what we do is actually that we take the process as defined before. So this actually is exactly our process ytn. And additionally, we go to the next point. So this here is added at the next point at which the process jumps. So here, if t ranges between these two values, j minus 1 over n and jn, at this point it takes exactly this value. Then this process here stays constant over the whole interval, and at this point it will jump then to its new value where this term here gets added. And here by this representation, so this is increasing from 0 to 1 linearly over the interval, and that gradually adds this value rather than just adding it in one go at the end of this interval. So this gives exactly this piecewise linear continuous representation. And the question of course is, does that change anything in the limiting behavior? So firstly we see, as explained, that this process has continuous sample paths like the Brownian motion, the limiting process. Further we can see that the difference between the processes is exactly this point here, and this converges in distribution to 0. So more precisely, we can show that the probability that the supremum over all t from 0 to 1 between the two processes is larger than epsilon. Now, from the picture that has been drawn here, it's clear that the difference between the red line and the yellow line is exactly attained at one of these points where the origin process has added or subtracted a new value plus or minus 1. So this means that this supremum is attained at one of these values, and there the difference is exactly one of these xj over n. One of these. So that means this probability over the supremum equals actually a probability where we look at the largest of the n values, xi over square root n, being larger than epsilon. And so the xi's are our standardized steps plus or minus 1. And the largest value being larger than epsilon means that at least one of these xi's must be larger than epsilon, and we can, so that is here actually the union of the events where one of the xi's over square root n is larger than epsilon, and the probability of the union can be bounded by the sum of the probabilities, where we now have xi over square root n being larger than epsilon, and as all the xi's are independent, identically distributed, we can write that immediately as n times the probability, and using Chebyshev's inequality we can actually approximate that as x1 over square root n square times indicator where x1 is larger than square root n epsilon. So here this can be expressed actually as an expectation of an indicator function over this event, and where this indicator function is 1, we use this here as an upper bound, and where it is 0, this value here is also set by this indicator function to 0. So then we, as here in the expectation, this square root n is fixed, we can pull it out, and it cancels with the square exactly with the n here. So we get finally the expectation of x1 square times indicator of x1 being larger than square root n epsilon. Now we have finite variance for the xi, so which is actually 1. So this sequence of random variables is dominated by x1 square, which has a mean. So correspondingly, this sequence of means is converging to 0 as the limit here of these distributions with this indicator vanishing as x1 asymptotically cannot be larger than infinity, which is here the limit. We have that this here converges to 0, and by dominated convergence we have that the mean converges to 0. So that means that here the difference between the two processes not only pointwise but actually uniformly converges in probability to 0. So we can treat these processes as complete process basically similarly, or at least asymptotically. Both will be will converge to a Brownian motion. So as another example, let's look at the Poisson process. So we know that the Poisson process has in common with the Brownian motion that it has stationary and independent increments. Now, having independent increments, we can actually use the increments of the process as the xi's to which we then use the function from which we form the partial sum process, and then can apply the function essential limit theorem. So we have here the random variables x and j, which is an increment of this Poisson process over an interval of length 1 over n, and that is then Poisson distributed with parameter 1 over n. So the mean of these random variables is 1 over n, and the variance as well is 1 over n. That is, these are the mean and variance of a Poisson distribution with parameter 1 over n. So if you then look at the process yn t, which is 1 over square root n, sum I equals 1 to the fraction tn of the xni minus 1, so 1 over n. So we standardize these random variables. So this is subtraction of the mean, and this is then the division by the standard deviation. So in principle we have here standardized random variables which we sum up. So in total this implies, or the question is, does this imply by the functional essential limit theorem convergence to the Brownian motion as processes? So it should be clear that this of course is not the case, because if we use, so for n to infinity, what we do is that we take our Poisson process and we partition it finer and finer. So these steps here stay Poisson distributed, but the rate becomes smaller, and we get more and more of these Poisson distributed random variables, which summed up are still the Poisson process over the whole interval. So if we then also look at the fractional process here, we actually have our Poisson process. So our ytn converges to the Poisson process at time t minus its expectation divided by square root t. And that of course is not a Brownian motion, as we have here a Poisson distribution which is piecewise constant and has, at least here in this part, an integer scaling. And this actually here should have been, just to mark it, this would be the scaling over the whole interval, but that was length 1 for our Poisson process here on that interval. So that was a mistake. So we simply have the Poisson distribution here corrected for its mean. So this gives a piecewise constant function here minus a linear trend. So we have in total decreasing, linearly decreasing process, which at random points makes jumps upwards by values +1. and definitely that is not the sample path of the Brown motion. So we have station here in this representation the x and I are independent identically distributed. However, what it makes the difference to the Donska theorem is that we do not have an infinitely long sequence of random variables from which we form then for all n the partial sum process, but for each n we have a sequence of IID random variables, and as n increases, which of course here for this convergence needs to go to infinity, as n increases the random variables change. So rather than having the same Poisson distributed random variable, say of rate 1, being scaled by a constant factor or a factor relating to n, namely square root n, and by that reducing the jumps that are here in the integer valued random variable, we use different distributions, so we change the rate of the distribution here, but still have then integer valued outcomes. So here the steps we decrease for increasing n the rate of these xn's, but they stay Poisson distributed, so we have still integer values. So this leads us to the following generalization of the functional central limit theorem, which is the functional central limit theorem for triangular arrays. So we assume, as in the example, that we have independent and identically distributed x and I for every n, with mean 0 and variance being 1 over n. So the sum of the xi's for fixed n, the total sum of the variance of the sum is exactly 1. So that is the standardization that we want. At the right endpoint, the variance of the sum should be 1, as for the standard normal distribution. So independent identically distributed, mean 0, variance 1 for the sum are our standard assumption, and in addition we have this assumption here that the maximum of the x and I converges to 0 as n tends to infinity. Then the partial sum process yt is asymptotically distributed like a Brown motion. So coming back to our Poisson process, exactly this extra condition that we have, so the maximum of the x and j over all j, that actually takes the value 1, at least with the probability that the process over the whole interval has more than one event. If you don't have an event, then of course there are no jump points, and consequently all the x and j's are 0, and the maximum cannot be 1 or not larger than epsilon. However, if as soon as we have a single jump somewhere in the interval, then regardless of how fine we make the partition, as we look at the increments of the original Poisson process, the maximal increment will always be at least 1. Because somewhere we must have a jump, and at the interval that catches that jump we have 1. So that means that this maximum here cannot converge to 0 in distribution, as actually with some positive probability it stays away from 0. So this means that taking here this origin Poisson process of course does not lead to a Brownian motion, as a Poisson process simply is not a Brownian motion. Now in contrast, if we now look at a process with almost surely continuous sample paths and also that having independent stationary and independent increments. Further, E of zt being 0, and the variance of z1 equals 1 for standardization purposes. So in contrast to the Poisson process, we now assume that we don't have a jump process, but actually a continuous sample path process. Now, in that case, we automatically, by the functional central limit theorem, obtain a Brownian motion. So, in the same way, we can define the process yn t as being the partial sum of the x and I, and clearly this converges to the original process at t. Okay, that's by the definition that we have here. If we take all the increments smaller than t and add them, we of course get the value of the process at time t. Say, assuming additionally here z0 equals 0, so the first value, or well, starting at 0, and therefore any value at a positive point can be interpreted as an increment, and zt as well is the increment of the process from time 0 to time t. So with this we need now to check the conditions for the functional central limit theorem. So what we have, independent stationary increments, so we have here by that we have an IID sequence for every n. We have the right mean and the right variance, so the only thing to check is that the maximum of the x and i's converges in probability to 0. And this basically means that none of the random variable x and i's has the dominating influence on the limit. So unlike in the Poisson case, where we can say that the value of the total process, or the process at any point in time, is actually determined by just a few of these random variables, namely those that catch one of the events, while most of these random variables are plainly zero. So we can say that a few random variables that catch the events have a dominating influence on the limiting value, and that here in this case need to be ruled out. And of course the reason why this is not the case, so why this converges in probability to zero, is that we have continuous sample paths. So that means by continuity of a sample path, we have for all omegas in a set A, where the probability of A equals 1, so almost surely having continuous sample paths means that for all outcomes but for a null set we have continuity. So let A be the set for which we have continuous sample paths, so a complement will be a null set. Then by continuity, for all epsilon larger than 0, there exists a delta that depends on the outcome and on the epsilon that we choose, such that if the time points are less than delta omega epsilon away, then the process for that outcome omega is values of the process times t and s for that omega are less than epsilon away. And this is exactly the epsilon delta criterion for continuity of a function, and here we apply it to the sample path. It should be noted that because we have here a compact interval 0, 1, the continuity at every point, so we have continuous sample paths, the sample path is continuous at every point. That means that we have uniform convergence, and this delta omega epsilon is independent of the time points ts. So we can use the same delta for all intervals across our interval 0, 1. Then we can define the set A and epsilon as the outcomes for which delta omega epsilon is larger or equal 1 over n. So that means if in particular two time points are less than 1 over n away, then automatically the corresponding values of the process at these 2 points are less than epsilon away. So correspondingly, so firstly we of course can see by our property almost surely continuous sample paths, eventually, as for every omega such a delta omega epsilon exists, which is positive eventually for 1 over n and tending to infinity, 1 over n going down to 0. We catch every delta for every omega, so at least for all omegas in the set A. So we have here monotone convergence from below to the set A, which is the set of all outcomes for which we have a continuous sample path. And that, of course, has probability 1. So if we are now interested in the event that the maximum of yi over n minus I minus 1 over n is smaller equal epsilon, that should be actually z, so our original process, then this event contains actually the set A and epsilon. So this means here in this set we require that the function values of the process for any two time points that are less than 1 over n away is smaller than epsilon. Here we only look at particular time points given by the division of the interval 0, 1 into n equidistant periods. So this event is larger and implies that this must hold. Okay, so this is a smaller event and it has a smaller probability. Correspondingly, if we now look at the converse, the complement, then the complement of this event is contained in the complement of this event and hence has a smaller probability. So that finally implies that the probability of the maximum of zi over n minus zi minus 1 over n being larger than epsilon that is smaller than the probability of A and epsilon complement, which converges down to 0. So that shows that actually here we have our extra condition that we need for functional convergence of the process. So that means that this process actually so by the functional essential limits theorem said differently, so that this process converges also in distribution by the functional essential limit theorem to the Brownian motion. So that implies that zt, our process by which we started, actually must be a Brownian motion. So that actually shows what I only cited beforehand, that a process that has almost truly continuous sample paths and has independent and stationary increments, that this process must be actually a Brownian motion, that is due to the functional essential limit theorem, and which is a simple generalization of the ordinary essential limit theorem. And the extra condition that we need for functional convergence here is ensured by the continuity of